Finally. Okay. Okay. Nice. Hello everyone. This video is about two vulnerabilities in the LLaMA.cpp RPC server. The RPC server communicates with a CLI client in a proprietary protocol. One of the things I noticed was that they allocate data and then give you, the client, the address of the pointer in the response. You then need to take this pointer and provide it in your next requests as a reference. At first, I thought that they didn't put effort into security at all. However, when browsing through the source code, I could see some sanity checks that prevents out-of-bound access. So it made me a bit confused. I mean, you give the client addresses from the heap, but then you add boundary checks to prevent memory corruptions? Looking at the fix made some things clear. They added a disclaimer saying that this server is in POC or development stages. The fact that it wasn't documented until now made me wonder how many people use this without realizing this is still not ready for production. In this video, you'll see the stages of exploit development, from getting a leak to overcoming aslr, crafting primitives, and popping a shell, of course. Well, hello everyone. Today, we are going to take a look at two vulnerabilities that were found in LLaMA.cpp. Now, I started working on it, but I stopped at the beginning because I then remember that I want to record it. So this is what we're going to do. First of all, I'm going to share with you the bug details, and then we will do an overview of what is LLaMA.cpp. And by the way, don't worry, I don't know anything about LLMs too, so if you're not familiar with this, we are on the same boat. And the third thing will be a recap of everything I did, and from there we will continue with my goal, which is weaponizing those vulnerabilities. This is two vulnerabilities. The first one is arbitrary read, and the other one is arbitrary write. So those are very, very powerful primitives that we can achieve RCE pretty easily using those primitives. So let's start with the bug details. We will go over the arbitrary write later. Let's just focus on the read first. Basically, what it says is, it's a very funny vulnerability actually, but I thought that it's worth covering. Essentially, what they are doing is that they are allowing you as a user to pass a pointer. Yeah, there's a structure or an object called RPC tensor or whatever, and one of the fields of RPC tensor is data. So you can see here, where is it? Data. This is a pointer, and all of this is inside a user controlled data, like packet. Every packet you send, you can include an RPC tensor object. So that's pretty straightforward. Arbitrary read address. And by the way, I have to give credit for this guy, the reporter. His name is 7resp4ss, or and Guangong from 360 Vulnerability Research. And essentially, they wrote a report or an advisory. I don't know who wrote this. That it's probably the most detailed advisory I've ever seen in my life. So I have to give respect for that. What they say is, like I said earlier, that you control is pointer, and they also include all the call chain, like the stack trace, from the moment that you start the RPC server all the way to the vulnerable mem copy. And they also wrote like a POC, which is very nice. Yeah. Now this was the bug details. Now a short overview about LLaMA. Again, this is gonna be very short because I don't know anything about LLaMA, but I do like memory corruptions. So LLaMA basically is like an open source LLM, I don't know, engine or interface, if that's what it is. The point is that they are allowing you to run LLM on your local host or on your, I don't know, on your server machine. And one of the features that they have is you can host an API server or an RPC that will act just like, I don't know, ChatGPT or whatever other AI trendy products, I don't know, chatbots or whatever. By the way, if you are like an AI expert and you're watching this, I'm sorry. I'm sorry for my poor knowledge in AI. But anyway, like I said, the point is that they have, like, one of the things that they develop here is a server, and this server is exposed to the internet, and we like that because we are hackers. So this, I didn't went too far with this, but we will do this together. So the first thing I did was to document like the bugs and the fix. I found a fix, and you can see the fix here. And it's also funny that they added like a note in the README of the RPC server that says, this example and RPC backend are currently proof of concept development stage. As such functionality is fragile and insecure, never run the RPC server on an open network in a sensitive environment. So they, with the fix that they added here, they also added like useful documentation. And it really made me curious to think, how many people use this RPC server? Because they didn't know that this is like an experimental thing. Yeah, this is interesting. So anyway, that was like the funny warning that they added. But apart from that, you can see here that they added, where is it? Like a bound check or something. I hate those diffs. I need split, not unified. Okay. Now, okay, this is just a const. There it is. Like it checks if the offset plus the where the data points to is like, it's like bigger than the boundaries, then you will abort and you will say that you detected an out of bounds access. which I'm not sure if that's the way to mitigate it, but we're not gonna discuss this now. Also because I don't want to drop 0 days live on stream. So we're not gonna try to go with crazy exploits. We're just gonna stick with the 1-day vulnerability here to see the impact and try to weaponize it to make it more than just a POC, but rather an actually a full exploit. Yeah, so that was part of the recap. Yeah, okay, so like I said, I collected information about the vulnerabilities, and then I reviewed the fix to know where I should be focusing on when I look at the source code. Yeah, and that's like line. Yeah. So like I said earlier, this is in a RPC tensor object, and if I go in the source code to the place where they attached the fix, we can see that it's in a function called deserialized tensor. And as hackers, we love deserialization functions because this is the root of all evil. Yeah, this is like probably the object that we control. And where is it? Find. There it is. Like it's doing a casting of the tensor data, and we control this value here. And then this result data will be a pointer to an arbitrary address. And if we go up the call chain, okay, that's weird. If we go up the call chain, we can see that from main, it's calling to start RPC server, and start RPC server, we have the main loop that serves requests. You can see that this is an infinite loop. It accepts a connection, and from there it continues to RPC serve client, and from RPC serve client there is a very interesting set of commands. So yeah, you have like a set of commands. We will come back here because this is a very important function. Like I'm doing this as part of the recap, and this is where we get into get tensor, and from get tensor, we take the incoming packet, which is the input, and I'm sorry, get tensor, which is the input, and you take the data and you set it as a pointer to RPC tensor. This is where you're doing the I don't know if it's called dangerous casting, but yeah, this is like where we put our input into use. This is where our input turns into a tensor object before deserialization, and this is where it's being deserialized. And then here you are yeah, like I said, you're taking the data pointer. Let's go here. Yeah, you're taking the data pointer of this tensor object, you're putting in the result data, your return result which comes back here. And then you call tensor get. Now remember, at this point, the data pointer has a value that we control. And every time we call tensor get, we have the get tensor function, which you can only know the value of this dynamically because this is a function pointer. No, I don't need to cross-reference this or even like debug it to see the value. I have it here. He provided the whole. Yep, there it is. So we were here, right? GTML. Yes, and we couldn't know the value of that because it is assigned dynamically during runtime. So that is what they put in get tensor. Let me see. Yeah, this is what they put in get tensor. So yeah, and this is just a plain meme copy from the tensor data, which we control, and data, which is the buffer. Okay, so that was the recap about the vulnerability. And this was also like a bug details, but also a recap of everything that I have seen. Now, the thing that I saved for later is that it was the loop. Let's see the loop. Earlier I said that we'll keep it for later, because this is the last part of the recap before we actually start writing the exploit. So like I said, here we have the main loop of the server where it accepts connections and handle like the incoming data. And we can see here that I noticed that they have a weird format for their packets. Essentially, the format is something like here they accept 1 byte, and then where is it? Input size. No, 1 second. CMD. Yeah, so the format of the packets is CMD, which is 1 byte. Oh, shit, 1 second. Okay, CMD, which is 1 byte, and then you have size, which is 64 bits. This is like 8 bytes. Yeah, and then followed by 8 bytes of size, message size, followed by the message itself. Which is very friendly, I have to say. And another interesting thing was that I saw the commands that this RPC server supports, and this is wild. Like, I don't know, as a hacker, as a CTF player, it's very fun to see commands like allocate buffer and free buffer, get and set. This is where our arbitrary read and arbitrary write primitives will be used. Yeah, so this was just something I wanted to share because it's pretty convenient. It's like almost RPC for primitives, not RPC for procedures. Now, yeah. So with that being said, let's write something that triggers this bug. Send message. Okay. What port is this? Localhost. Let's say IO send. Yeah, like that. And then just see all. Let's see what it prints. Oh shit, I forgot. No. I forgot. Let's do it like no. Yes. Okay. RPC RPC server. Okay. And now we're gonna run hacks. Oh shit, I didn't. That's stupid. Send message. Okay, it's doing something. Yes, I had a... How do you convert this into a byte? Is this a real thing in Python? Okay. Terminate code after throwing instance. Okay, alloc buffer. It's like 0. So you can say, let's look at it again. First is the CMD. And then we have the message size. Oh, I'm sorry. Brackets. Let's do send command. And then you said that the command is U8 RP8 command, and then packets P64, and then packet, no, then buff, and then packets buff. Sandy. Message size 8 bytes. Content. Right. Now, oh, okay. I'm sorry, I forgot. CMD. So you can nice. Okay, debug. You didn't receive anything. Just 0B. But this is the response. So I'm supposed to get a big response out of this. And not only, like, one of the things that I saw was that you can get a pointer out of this because they pass pointers in their packets. You see output, data, and then so you say alloc buffer with size. Oh, no, I'm sorry. I didn't. No, I'm stupid. This will not give us a leak. Remote size, buffer size. It just allocates a buffer and puts whatever we send to this buffer. That's not good. So how can we buffer clear? Okay, what is copy tensor? What happens if we No. Is there like a generate tensor? What is get device memory? Output serialization for free mem. No way. Is this what I think this is? 2 times. Total memory. Oh no, it's just those two. No, it's not. It's not a leak or something. Get base. Remote pointer. You have buffer. Okay, that looks good. What is get base? Buffer context. Okay. And buffer is no. No. That's not good. Remote pointer. I don't want to provide a pointer because even though I have like very powerful primitive arbitrary read and write, the first thing I need is something like out of bound or something like to get a heap leak. This is what I want. A heap leak or any kind of leak. So I will know what. I just need to get one valid address in the memory space. And from there, the arbitrary read and arbitrary write primitive are very powerful. But first, I need to know what I want to read and or what I want to write. So we can. What if you allocate that buffer? Oh shit, input size. I thought about like asking for a very big size, but not filling the message with the bytes. And then the next time I read this data, I will get like uninitialized heap data or something. Oh, maybe it's fine. 1 second. Yeah. Wait, what? Remote pointer into output. Is this? I think I don't need I think I don't even need to. One sec. Maybe the connection is like disconnecting too early. No, okay, no, it's not. Okay. That is weird. I need to get the remote pointer here. You can see remote pointer and then remote pointer. Output serialization format. Why? I'm not getting. What do I miss? You get one size of command, and then you get input size, and then you get the data. I'm pretty sure that alloc date, alloc buffer, which is 0. And then 1, 2, 3, 4, 5, 6, 7, 8, which is the size, 6 characters. And then you have 6 characters here, like 6 bytes of information. Alloc buffer. What is this? Oh, maybe it's like, maybe okay, get false. Okay is not checked here. And if okay is false, then we will break early and we will not get a response. Probably because our packet is, I don't know, corrupted or something. Input size not equals to size of. Okay. So it needs to be like 8. Let me see now. Oh, no, I'm sorry. Now let's see it. Cool. But we still didn't get fit to allocate buffer of size. What? What is this size? Is this like 61, 61, 61? Let's. Yeah. Oh. Oh, I get it. Like the content. When you request to allocate a buffer, you specify size of the buffer you want to allocate. This is the size of the message, and this is the size of the buffer you want to allocate. So let's, you know what, let's do it like that. Alloc. No, let's keep it like. Okay, so whenever we 0x20, this would be the size of the chunk. Cool. Damn. Now we have a heap leak. What? What? So after we allocated a buffer, like you have 8 and then another 8, we can resp and then keep leak from the 8th byte until the 16th byte, and then we'll just use 64 and log info. And now let's see it like that. No, that's wrong. Oh, that's weird. See. Okay. Cool. So it was because of the receive all. Nice. Why is that? So sometimes it fails to allocate, but okay. So now that we have the heap leak from this get, I don't know, alloc size and come on. Alloc buffer size, right? And now, yes, okay. Now, we can use the arbitrary read. Get answer is 7. Set answer is 6. Six, 7. And now that we have get tensor, or maybe like arb read. Come on. No. Send cmd, and then we'll say get tensor. tensor. Right, so you have inputs. Input size of, oh wow, that's what? 128 plus 16. So this is a total of 138. And then how do you do this? If you have, I think it's called flat args length. Okay. Or no, I'm sorry. This. And RPC tensor. In tensor. So what is the offset? No, what's offset? Size of offset and size. Is this the same? No. Size of offset, size of side. Okay, so it copies the last two keywords are, oh, it says here the last two keywords are offset and side. Now I feel stupid. Let's do it like that. Tensor. And then we'll say like from, I don't know, like 30 AP64 offset and 38 is, I don't know, size. And what is the offset to data? This is 4 bytes. This is 0x40. So 440, 0x4, and the size of this is 296. That is the offset. Let's see. I doubt that it's going to work. It should segfault. A flat does not fit argument within length. Flat argument does not fit. What? Oh, maybe because. Oh. It's like that. Okay, let's. Cool. Oh, segfault. Nice. Nice. Okay, let's try to debug that. GDB, and then run, and then this, and now we see that REX is not good. Why? What? No. Maybe I had like no. I'll read. That is really weird. What? No. Yeah, that's E0. Then 1, 2, 3, 4. Oh, I was wrong. It's E8, not E4. I mean, it says that it's packed. Like it has a packing and alignment of 1 byte, but for some reason, oh, padding. What? Like, why would you even pad if you use pack? Never mind. That was weird. I'm sorry. So yeah, I needed to add just 4 more bytes. RX. Come on. What now? What now? Okay, E8. Yes. That's like what? What? Context. New input. Oh. Deserialize the new tensor 4D. I think, yeah, I think we need to set more fields. It fails here because the type of the tensor. What is the type? It's like 0. So let's say that the type is as an offset 8. Offset 8, you would have this. Maybe if we enter an invalid number. No. Come on. It's crashing here. It's crashing too early. GGML row size type. So be the data set. What happens if this function fails? Result. Okay, no, we need it. This is gonna be the return value. NE0. What the fuck is NE? 64 good beef. How about now? You're in 32. Those are 64. What? That's weird. Now let's just start guessing. This is and offsets, and RC tensor. Okay, we are going to debug that shit. I fucking hate it. $78. Now I'm going back to the deserialized tensor and the return value. Oh, you allocate like it was successful. It was successful. Okay. So if that was successful, set name. Can we finish this? Oh, no. Okay. We're supposed to get result. What? Free? You don't have free here. Get tensor. Deserialize tensor. Get tensor. Oh. No, that's not good. So we're going to hit this. Because tensor is a null pointer. R12. Yeah. That's not good. So why it returns a null? Who used that? Insert. Oh, an alloc buffer. I knew it. It's an alloc buffer. So what we're supposed to do is buffer is after type. Heap leak. Heap of valid other. Int. Alright. And then here we're gonna say keep leak. I think let's see. Finish. That's good. Now to finish. IRIX. Right. Okay. Okay. So if we do continue, we're supposed to hit the seg fault on address cafe babe. Let's see. No, we're not. Why? Why? compare. Okay, so we skipped that part. Maybe like resize. We are almost there. Almost there. HTML backend. Yeah, it's almost there. I think it's here. Like output serialization format and then data bytes. I think this is because of the resize. Here we said that the size is 0x10, but here we allocated a buffer of 0x20. So if we do keep it like consistent, run, delete. No. Okay. Okay, that's where we need to break. So we reach here. We reach here. Yeah, this is where. Oh, I think I know why. Then What's this? RDI.
1 hour later.
So all we need is just like we had a mistake of 8 bytes. Where is it? Target address E0 maybe. RCE. Cafe Babe, nice, very nice. Okay, we really need to. Contours flat. By default, there's a cyclic. Customize this by providing an iterable or method. Nested dictionaries. That's weird. I swear I tried this. It doesn't work. It doesn't work. Flat. Oh, it doesn't work. Oh, it works because I don't have an error. Okay. Okay, and 5F is probably underscore, like the letter underscore. Let's see. Yep, it's underscore. That's weird. Okay. No, what? No. Sensor good. Abort. What happened here? Operation not permitted. What? I don't understand. That's weird. What? Is seeing tensor readout of mount. Why? Oh, I'm sorry. I made a mistake. It should be smaller than or equal to the number of bytes sent. So this, now what? Are you joking? Is this a joke or something? Offset plus size is less than GGML bytes tensor. GGML byte tensor is, oh, it's those NEs. That's stupid. Okay. So what offset? Like 8. 4. 12. 20. Okay. So at offset 20, you should say number of elements 4. Two, three, 4. 1, 2, 3, 4. 4 times. Now let's see. Unpack requires a buffer of 8 bytes. Okay, that's just. Oh, nice. Okay, now let's attach GDB. Maybe run. Nice. Cafe babe. It's still not perfect, but it's a very good progress. Like I need to do like that, I think. It's what? No, not again. Data not equals to. Come on. This is valid address. This is target address. So oh. Hmm. Why it takes only the last bytes? Like, why? 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 128. You know what? Do this. Let's see. Oh my god. Oh no. Oh no. I'm stupid. It's the offset. Foo. So it's like 1, 2, 3, 4. And then you don't need all that. You also don't need. No, you need that. Okay. That's all. Enter. And what will happen is we ask to read this address. So it will take those bytes, put them first, and then take the offset and put them in the other 32 bits. Nice. Okay. We got it. Oh my god, that took time. So if we want to read a target address, we one, two, three, four. 1, 2, 3, 4. And the offset would be 1, 2, 3, 4, 1, 2, 3, 4. Because like that's the first 4 bytes, and this is the last 4 bytes. Now if you want to do did beef cafe, we can use that. Doesn't look good. Why? Adapter no. Okay. Okay. You know what? Just keep it. Just keep it like that, man. I'm not trying to fix. Thank you. No, it's not good. It's cafe. Well, it's supposed to be dead beef. Cafe. Okay. So 32-bit shift right. Now let's see. Oh, finally. Okay. Whew, that was frustrating. Oh my god. Dead beef cafe. And then you say dead beef cafe. Okay, so now we can see like RCE. Okay. So we have leaks. Nice. We have arbitrary read. Wow, that was frustrating. Oh my god. So we can like take this. No, actually, 4 and I don't know, 20. No, again for then you can say rasp I times 8 times 8 plus 8. U64. Okay, now let's see. Receiving. Oh, I'm sorry. Okay, try again. That's nice. We have leaked memory. Okay, I'm gonna take a break now because it's like 2.5 hours already. I'll be right back.
The very next evening.
Hello again, everyone. Yesterday, yesterday I fell asleep. I accidentally fell asleep, and then today I had to work, so now it's evening, and we're going to continue the RCE exploit. Yesterday we managed to get an arbitrary read and a heap leak. And today we are, I don't have a lot of time like yesterday, but we are going to craft the arbitrary write primitive. And after the arbitrary write, we will think about what we should overwrite in order to achieve an RCE and weaponize those two vulnerabilities. So let's look at the arbitrary. The first thing we did was to look at the arbitrary address read. And we noticed that there is an unsafe data pointer. Now, the funny thing about the write primitive is that it is also using the unsafe data pointer. So I think what we need to do is, just like we exploited get tensor, we will exploit set tensor. But there will be a small difference because we are writing. So let's do this. And look at the code. Okay, so it's like data. It's the same followed by the data, I think. RPC tensor and then offset. Is the same. Okay. Um, Oh, so you do have offset. Wait a second. What? Size. Let me see it again. So here it checks whether it's RPC tensor plus in tensor, D0 tensor. Data is input data plus RPC tensor offset. And then size. Data. Okay, so data is everything that comes after the RPC tensor object. And after the offset. So it's here. Okay, so that's correct. Node. So set tensor. Right. I think that's it. Is it gonna be that easy? I don't know. I mean, let's check it. Yeah, it's that easy. We're trying to write a QQQ, and we are writing the payload that we control. Nice. That took exactly 8 minutes. Nice. So what now? I didn't expect it to be that quick.
A few moments later.
Okay, so we have arbitrary read, arbitrary write, and now we need to leverage that to get remote code execution. We can use a function pointer. In every tensor command, those are the commands. In every tensor command, there's a function pointer call here. In this interface, it has this, and then all those function pointers. So set tensor. Okay. We will put bin sh here, and then we will call get tensor or set tensor, and we will overwrite one of those function pointers. Yeah, so what we need is the address of buff, and we already have it, which is pretty convenient. We already have it here. I mean, this is where we get when we call alloc, and then we get a response. In the response, it discloses for us the address of buffer. If I'm not mistaken, let me just make sure that this is correct. I assume this because if you can see, this is the output, and you copy the address of, you copy 8 bytes, which is the remote pointer, and the remote pointer is the address of the buffer. Yeah. So when we are doing set tensor, heap link. What is the offset of this thing? Where's the function pointer? Oh, jump rocks. Maybe it's this. Yeah. So the offset is 0x20. 0x20 supposed to be this set tensor. Yeah, it makes sense because 0x8, 0x10, no, 0x0, 0x8, 0x10, 0x18, and then 0x20. Yep, that's the offset. So 0x20 is set tensor. And then we will call again to set tensor. But with a, it's supposed to crash because it's supposed to crash. No, I don't want to comment. It's supposed to crash not because we are writing to dead beef cafe babe. It will crash because the function pointer of the set tensor is corrupted, and the contents of this function pointer will be 0x51, 51, 51 if our attack works. So let's see this. I feel like I forgot something. Well, let's just run it. Oh. Okay. Yes. And what is RDI? RDI points to yeah. Okay. So we right. Yeah, RDI is our heap leak. So here we will put bin sh. This is the beginning of bin sh. All right. And then one more time. No, what? Where am I? Okay. Nope, not good. Why? Oh, because we need to do it like that. I'm sorry. Run. Okay. Nice. Okay. That's good. So, now we need to yeah, I'll just no, we don't need this. Let's just I know if we are overwriting this, let's start with a leak. First, we will leak the address of set tensor or read. All right. Set tensor address, and then what? Okay, and then lib. Wait a minute. Do they have system maybe already in the global offset table? No, I can't see. Never mind. So what I was going to do is GML. Come on. So it's like here, and this is the base. So if you want the offset from, where is it? This to the base, which never changes. I mean, between builds, it will be this address. Lib gmml base. All right. It's supposed to print an address that is like rounded. What? Oh, I'm sorry. Alt-buff, then arbitrary read, and arbitrary read, it's returning 0. So okay, so what is no run it again. Like, what is the structure that output? Where is output? Okay. So if you read this, what? No. I think this is set tensor. Yeah. So according to that, you're supposed to do U64 and then RESP 0x8, 0x10. Now, let's see this. Oh shit. Not good. Set tensor. Let's try again. Oh shit. Okay. Back in CPU. Right. And that. Okay. Cool. Now it works. I don't know. I just got the wrong offset for some reason earlier. I just want to make sure that it works, like, even without a debugger. Yeah, that's nice. We always getting an address that looks good. It looks page aligned. Like even if it changes, or not, it's never mind. I'm just missing my point here. Yeah, it changes. It changes between every time you run it, it changes. Okay, now back to the debugger. So we know the base. And that's weird. Maybe I had a typo or something. Yeah, okay. So, oh shit. Okay, wow, that's more than I thought. I don't know, for F and print F. Okay, let's just overwrite. I mean, let's not overwrite. Let's read. Let's read. Something from libc. Like on a stir comp or put char. Let's read put char. Nope. Oh, I'm sorry. Oh, the butcher offset. It's not butcher offset. You need butcher got offset. Then you say the base. Yes, that's what you need to do. Butcher Oh, I'm sorry, this is the global offset table of. No. Okay. This is the base. That is the offset. Does that make sense? Let's see. Nope. If you could put your. Why not? Oh. What? You read from the base address plus this relative offset. That's what you read. No. No. Let's see. Maybe it's not resolved yet. Okay, let's try another one. Let's try. Stir loop. Maybe stir loop is. Okay, now let's see. Man, I didn't do like, this is some CTF type shit. I didn't do this in so long. Oh god. Got, and then got PLT. What does that? Yeah. Okay. So you see, we do have some stuff. Okay, you know what? I have an idea. Telescope. This is the base. Where is the... Come on. Okay, let's go with this. Here, we will use STR talk, which is part of libc, I hope. Yes, it's part of libc. Oh my god. Okay. So, STR talk. STR. Talk with a Q, right? Okay, that's weird. fprintf. Good. fprintf. And then we're doing no, that's not good. That's not libc. That's still what the fuck, man? Like, and this one, yeah, this one does. Puts. Okay, it uses puts. This happens because the first thing that is being loaded into the global offset table is just a trampoline. This is why you see a lot of time that we hit the PLT. It's like a small trampoline that the responsibility of that trampoline is to jump to libc, resolve the function, and then update the global offset table. Now, it's not updated unless you call it. So the initial state of the global offset table is just a lot of pointers that's pointing to all those trampolines. But once you call them, the global offset table will be updated. So as you can see here, those two functions are probably I don't know, common or like called very early. So they are already resolved, and this is why here we have libc pointers. So we'll just go with puts. Come on. Okay, excellent. And now that's the offset of puts. And let's see if it works. Okay. Very nice. Puts and libc base. Nice. So now we know the address of the base address of libc, and we already know how to take over the instruction pointer. Now the last thing that we need to do is to calculate where system is. Now, depending on the libc version, you can determine the offset can change based on the libc version, but you can determine you can determine remotely the version of the libc that the remote host run using a tool called libc database. I mean, we're not going to use this because we already know the version of the libc here locally. But just in case you want to exploit a remote server that you don't know what libc version it runs and what are the offsets that you should use, you can use tools like that. You would just give it the address of puts, and it will give you possible versions of libc that the remote host is using. Yeah, and then from there you can know where system is located. So that's a pretty nice method. But like I said, we're not gonna determine blindly what is the libc version, because we are exploiting ourselves. So we already know what is the distance. Yeah, so system and the offset between system and the base is this. Base. System. And now we're going to use this PC takeover that we did here. We're going to put bin sh. Instead of q, we'll put the address of libc system, and then we will call get tensor to trigger the jump box. Yeah. And then interactive. Okay, so this is a moment of truth. Let's not open this in the debugger. And will this work? I have a feeling that I forgot something, but let's see. I knew it. Okay, let's see why. I was too optimistic. Where is it crashing? bin sh. Code cd. Okay. If we do this. Okay. Now I'm going to do run again. libc system. Okay, that's weird. One more time. Oh, it works. It's just not deterministic. Okay, it works. It works. But it pops the shell here. That's funny. It pops the shell on the server side and not on ours. Yeah. Okay, so let's try again. Now this is the moment of truth. Okay, not yet. Oh, I think I know why. I think I know why. We need to add like just one more. Like connect, disconnect, and then trigger the vulnerability. Set get breathe. No, I'm sorry. Alloc off. Yes. I'm connecting, allocating a buffer, disconnecting, and then doing all the exploit. I'm doing this because I want that the how do you say it? Like the global offset table that I talked about earlier, I want it to resolve the address of puts. And in order to do this, I'm just going to connect to the server, do some stuff, and then exit, and it will probably like print stuff or whatever. So that's the reason I'm doing this. So let's see it now. Nice, it works. The only problem is that the shell pops in the server side, but it's not an issue. I mean, this is a good issue. So all we need now is just to take this payload and change it to something else that will connect to the remote host and send all the output to there, like a reverse shell. So I think that's it for today. It was really nice. I enjoyed this task. Yeah, it doesn't work. So thank you for watching, and I hope this was informative. Maybe, I mean, now it's midnight, but maybe later I will just modify this payload to make it like a reverse shell or something. But at this point, I'm too tired and it's already too late. So yes, that was it. I hope you liked it, and thank you for watching.